It's a real pleasure for me to welcome Melisa Orta Martinez here to the campus today. We have I have the honor of being a collaborator of hers on an NSF-funded research project, and tomorrow we're going to be spending a lot of time delving deep into that. Looking forward to that, but Melisa agreed to sort of give us a talk today. So a little bit about Melisa. She is an assistant professor in the Robotics Institute at Carnegie Mellon, and she leads the Social Haptics, Robotics, and Education Lab, SHRED. There it is, awesome logo. And so in that lab, she focuses on developing low-cost, open-source robot technology with education applications, understanding the impact of this on education. And so she's going to speak to us today about that. Prior to being on the faculty at Carnegie Mellon, she was a grad student at Stanford in the CHARM lab with Alison Okamura. So got a thing with really well-named labs. And prior to that, she was an engineer at Apple, where she worked on the haptic feedback for the trackpad that many of you use on your MacBook Pros and so forth. And prior to that, she did her undergraduate work at Tec de Monterrey in Mexico, where she studied electrical engineering. So, Melisa, thank you so much for being here. We're looking forward to your talk.
Yeah, thank you so much. So as Ed mentioned, I'm a new assistant professor at Carnegie Mellon University in the Robotics Institute. And today I want to talk to you guys. Well, we can have a discussion where you can interrupt me if you have questions whenever about some of my work, which focuses on using or how to design robotic interfaces for educational applications, and what might be some of the applications of these robotic interfaces. Now, in order to do that, I first want to start with a little framing to motivate it. And so I think we can all agree that math is really hard. For most students, it's really hard. And it's really this subject that presents kind of like a gateway for those students. A lot of students, if you talk to them, the reason why they didn't go into STEM is because of math, or they believe that they're not good at math. And so there's a lot of problems with how we teach math that I don't want to get into. Like there are people who believe that either you're born with the math gene or you're not born with the math gene. And if you're not born with it, you just can't do anything about it, right? So we're not going to talk about that today. But what we are going to talk about today is this other belief that exists in math, which is very weird to me. And I'm going to explain why. But this kind of belief that the progression, or like the real progression of math, should go from concrete, so stuff like you see here, where when you're young, you get stuff to play with and to do math with, and then to abstract. And that actually, if you're smart and if you possess that ability of higher thought, you're thinking abstract, right? And so I know a lot of us are engineers here, and you probably did very good in math, and you probably are very proud of the fact that you did very well in math. And so I don't want to take away any of your accomplishments, but if you allow me to, I do want to burst your bubble a little bit and reframe your accomplishments. And so in order to do that, let me use an educational framework called constructivism. And so we don't need to go into depth of cognitive theory, but I want to run through it very fast what it means. So basically, constructivism is this cognitive theory in which the belief is that, number one, a child or a student will actively construct their worldview. Number two, that you can't really think about something without thinking about someone thinking about something. And number three, that concreteness is not really a property of an object, but rather a property of a person's relationship to that object. And so why is that important for us? Well, if we sign on to this theory, this cognitive theory, then objects that are considered abstract can become concrete, regarding that we get into the right relationship with them. And so the more ways that we have of interacting with any objects, the more relationships we make between different objects, the more concrete it is going to be for us. And so concreteness then really becomes a property of the relationship, or the type of relationship that we are going to have with that object. And so what does that mean for math? And so let me give an example in how constructivism is being used in math today. And so in the example, I want to base on fractions. So fractions is one of those subjects that really kind of divides students. fractions is considered very hard for young students. And the difficulty lies in that young students really don't quite understand what that whole is. Like why am I doing a fraction? Why am I dividing thing? What is that thing that I'm dividing? And part of the problem is the way we teach fractions. So really, if you think back to your days, and maybe no more Gen Z, but like my days, if you think back how you learn fractions, you really learn rules on operating on fractions, right? Like you learned that, for example, like to add, before my common denominator, and that's how you can add. To divide, you invert and multiply, and that's how you divide. And through that, and through a bunch of repetition and doing problems, all of a sudden it just clicked together for you, right? And here's where I want to burst your bubble a little bit. Like, it's amazing. I bet it felt amazing once you clicked and you understood it and you were like, yes, I'm the rest of fractions, I understand it, and that's awesome. A constructivist theorist would say that was just a happy accident. And so a constructivist way of teaching the same concepts would be a little bit more what it looks like on the left as opposed to on the right, where instead of giving students rules on how to operate on fractions, you will give students multiple representations, both sensory, so things like pies, charts, blocks, things that they can touch and play with, and non-sensory representations, and then have multiple activities where the students interact with these, and then allow them to make their own rules for operating on that. So once it's very clear what the fraction is, and they have a proper relationship to it. All right, and so let's say that we do sign up to this constructivist theory. And so as roboticists, what do we do about it? Well, if we do sign to this theory, then we can think about that things that were considered abstract, things like math, could become concrete. And so it's interesting for us to think about, okay, so then how do we design systems to give students interesting interactions with these very abstract concepts so that they can become concrete for them? And there has been actually a ton of work on this already. One of the very first proponents of constructivist theory was Seymour Papert, and he invented the Turtlebot. And what he did was invent a robot so that students would learn how to program the logo programming language. He invented his principles, such as like, let's have the robot be open so students can witness the different parts interacting with each other, and started teaching students how to program at a very, very early age. And ever since he did that work, the field of educational robotics has really exploded. There's just too many examples really for me to name all of them. But I would say that most of the basic principles that he uses haven't really changed very much. There's still, so most of this, even though there's been a lot of innovation in these educational robotic systems, most of them are designed to teach robotics. So most of them teach you how to program. More advanced ones incorporate some sort of electronics work as well. So a few of them incorporate how to design some mechanisms for robotics, but at the end, you're really designing a robot that's, you know, based on educational principles to teach robotics. And so we're here to talk about math. So how about math? Okay, and so how about math? So why is math so hard, and what can we do about it? So with these robots, the one thing, it is true that like with these robots, you are also developing critical thinking skills, right? Which definitely help you in math. It's not like you're not learning anything about math, but you're not learning math directly. And so one beef that I have with the way we teach math today is once we get to higher math and we're expected to think in abstract, we're not really thinking in abstract. Like, you get an equation that looks really, really hard, and then the teacher will give you a representation that will give you something like this, and then we'll look back at you and see like, well, obviously. And you're like, well, obviously what? I don't know, I mean, I don't really get, like, right, just from like this equation that we get that graph, and now you somehow have intuition for similar equations. It's really, really hard. And so let's think about how we can use robotics to create representations of these equations that we can actually like play with and gain intuition from. All right, so the first representation that I'm going to propose is going to be a haptic representation. So I will posit that haptics is a very underutilized sense. We have tons of different receptors and sensors in our skin and in our muscles. Each one could provide a channel for us to communicate with abstract concepts and help us get more interactions and representations and help us understand these better. there has been some work in that realm. I think we can all recognize algebra tiles, which were given to us mostly to learn counting, things like that. But now actually there's researchers that are working on using these to teach higher math like calculus in a tangible way. Here we are to talk about how to use robotics. And so first, let's try and see how we can use haptic interfaces in order to render these abstract mathematical concepts. And so there's many different types of haptic interfaces. But if we look at kinesthetic type impedance haptic devices, well, you have like, you can have a very simple one. This is a 1 degree of freedom one. It's like a little joystick. And then you move it around, and what you get is you can sense the position of the user as it's moving in space. And then you control the force feedback that the user gets through the haptic interface. And so let's say, for example, that you want to behave like a spring. And so then all you need to do is say like, okay, so now the force that the user is going to feel is going to be proportional to a constant times the position. And now it's going to behave like a spring. And so that makes sense. And so many researchers have explored how to, how to use these haptic interfaces to teach physics. It totally makes sense. There's a simulation from Karen McLean's group in British Columbia, where it's on springs. And so what you do is you can experiment with different springs, change the stiffness of them, add them in series, add them in parallel, and then now, and with the little joystick, as you're moving it around, like you see on the screen, now you can feel what it feels like, right? So it totally makes sense to teach physics using haptics, because you're programming the physics, you feel the physics, you learn the physics, right? It makes sense. All right. But what about math? Could we do the same thing with math? What should math feel like? And so this simulation right here, where we asked ourselves, what if we wanted to teach trigonometric equations, right? And what should they feel like? So what we did is we made a simulation where the purple line that you see in the graph is the force that you feel out of the haptic interface, and as you move and explore the X direction. And so here, what's important to know is that you do have to be careful in like, what exactly is it that you want to convey to the students? What is it that you want them to understand about these functions? So here, our main point was we wanted students to gain an intuition about what changing the amplitude in the equation was going to do for its representation, for its graph, right? What does that mean? What does it mean to change the frequency? Like if you double it, do you actually feel like double the thing? Does it make double the thing? What does it actually do? Right? And then the other thing that they're getting is they're getting this little window right here, right there, where you also get the unit circle, and they can witness the unit circle. Now, so what we did is we taught these, we taught a class for high school students where these purple graph that you see was hidden from them. And so they would only get the feeling, they wouldn't get the actual graph. And then we asked them to explain to us different concepts about trigonometry. We asked them to draw different signs and cosines of different amplitudes and frequencies, and if they were able to interpret the haptic feedback and understand what it was. And so
if they were actively controlling the device, wouldn't the frequency depend on how rapidly they went back and forth?
Oh, that's very interesting. So the frequency at which they felt the feeling, but basically the texture that they would feel depends on where they are in space. So like if you have cosine of 2x versus cosine of x, it's gonna change as they move through the same point. It's gonna change how many bumps they feel moving through the same space.
Oh.
Does that make sense?
So what's in the lever? What are they experiencing as they move the lever?
So as they move the lever around, what they experience is so as you move around, this axis becomes force, and this axis is just the movement. So as they're moving around, so in this representation, they will just feel like these bumps, and in this one, they will now feel double the bumps as this one, because it has double the frequency. And in this one also, the amplitude is shrinked, so then they feel same bumps but with less amplitude.
So it's talking about spatial frequency, not time frequency. So how many bumps you feel as you move the lever from.
I see. I got it. Yeah, thank you.
Yeah, no, thank you for the question. Yeah, and so here, yeah, so what you're getting here is that in this particular example, what we're doing is we're using the haptic feedback to represent very specific concepts that we want the students to be able to understand. We want them to get intuition into, if I change the amplitude, like increase it or decrease it in a waveform, what does that do? The graph grows or shrinks, and it's the same with the feeling, shrinks or grows. And if I change the frequency, what does that do? Will I get more bumps or less bumps? And if I do a sine versus a cosine, it changes where the bumps are in space. And so you have to be careful. It's like exactly what. And now it doesn't. I posit that it doesn't have to be force. Maybe it could also be changes in vibrations or changes in other haptic effects. We used force for this one because we had that little haptic device. And so
they're feeling functions.
they're feeling.
At some point, are you then connecting it to their ability to understand math when they don't have that device there?
Yes, yes, so that's these are drawings like from the students. So after the session, we asked them to explain to us. So we did things with science, for example, and we asked them to explain how do you think a cosine would look instead? And then these are their drawings where they're like, oh, okay, so if it has amplitude of 1, it should be this big. What if you have the amplitude? What should it do? And then they would draw it, or like, what if you double the frequency? What should it do? And so, yeah. All right, so in that example, we're using haptics to represent a very specific concept, right? Now I want to talk about another way in which we can use haptics to help us understand math and to ground these math concepts. And so this is work that we have ongoing right now in the lab. It's not all complete, so if it doesn't work out, it doesn't work out. But now, how about polynomial functions? And now not just trigonometric functions, but let's talk about polynomial functions. And so when you have a polynomial function, right, and you're trying to understand what the polynomial function is going to be, then usually in math, the teacher will have you derive different aspects of a function, right? For example, for a parabola, they'll have you derive the axis of symmetry, the vertex, and those are sort of useful constructs. Like if you have a factorized representation like this one, then it's like, okay, yeah, I can see that. So the axis of symmetry is gonna give me very easily the shift in the x direction, right? And you're like, okay, that gives me some intuition about how to compare different functions or what different functions are going to do. And then if I derive my vertex, then that also tells me things about the shift in the y direction. So it's like, okay, those are useful constructs. When you don't have a factorized parabola equation or another polynomial, then it's a little harder. There's still formulas for it. And so most students will just learn to calculate it. They don't actually, it's hard for them to get an intuition into what it actually means. And it doesn't actually tell them much about the actual orientation of the parabola or how much it's going to open up. And it doesn't really help you that much to compare different polynomials to each other. Now, I'm going to, again, theorize that it's very important for us to have some intuition about these polynomial functions. Like, we actually use polynomials for a lot of things. We use them to try and model data, to interpret data, and being able to have some intuition about what every term in the polynomial does will help us not only construct these models, like should I add another polynomial to my fit or not? Am I overfitting? What am I doing? And to compare different sets of data to each other as well. So it might be very useful for us to actually be able to look at an equation and kind of like, you know, have a feeling about what it is going to do so that we can actually understand it. And so what we did is, and what we're trying to do in this project now is think about polynomials more in their general form as, you know, an addition of different powers of x, right? And then thinking about like, okay, like how can we give students intuition about what each of those terms is going to contribute to the actual graph? And it's actually quite hard, especially like the linear terms. Like, what is the linear terms like that quadratic, right? It's actually pretty hard. But then, so what we did is like, okay, what if we could create some sort of, imagine you have like a clay that you could play with and in space and like model equations with. And then through haptics, what we are trying to do is then encode each one of the terms of the polynomials in different gestures that you make, so that you can get an actual like embodied intuition about what each one is going to do. And so we created a very simple haptic interface and a not so simple clay simulation where we can control, so the clay simulation basically is based on a particle simulation, and we can control the physics of the particles, and so how they interact with each other, right? And so we can make something that's very, very goopy. And so if you're trying to mold something that's very goopy, think about like that goo, right? You're gonna make some motions to model it. And but if you have something that's very stiff, now you can like rotate it and tilt it and do different things to actually get it to where you want to go. And so, and in the spectrum in between, what we're observing is that users will do very different gestures and motions to mold, depending on what the clay feels and behaves like. And so we're trying to study how to try and motivate students to have very specific gestures for different terms to achieve different terms in the polynomial, and hopefully to encourage them through those gestures to understand what changing each of those terms would mean for the final equation, so that they can get an actual embodied intuition into what those polynomials mean. And so in this case, it's very different from the previous one. The haptics itself is not doing the equation, but instead encouraging the types of gestures that you might do in order to create these functions. Okay, and last thing. So last thing is very, very different from the previous two. It's not going to be haptics this time, but just plain old robotics. But in order to do it, I want to introduce a type of art that is actually very prominent that I didn't know about until I started talking to artists at Carnegie Mellon. But and that's the art of weaving. So weaving is really, really cool, and it's really mathematical, and I didn't know. But yeah, so it's been around forever. What's really interesting about weaving is that every culture in the world does it and has done it, and there's no real line of causality that has been established. Like we don't really understand, like they did it kind of in parallel. So people in the Americas were doing it, and people in Egypt were doing it, and and people don't understand how they seemingly didn't talk to each other. Also technology, and I'm gonna talk about this in a little bit in more depth, but our technology really has evolved because we are very vain and we want to wear clothes and we want to make better clothes, and that's why we invented technology. And so technology around weaving is very interesting. The art form is very interesting, and it's very, very mathematical. I'm going to explain how in just a second. All right, and so the way we create textiles and we create cloth is by interlacing some sets of yarns that run vertically at right angles with some other sets of yarns that run horizontally. And so usually to weave cloth, what you do is you have your warp, which are the yarns that run vertically, and then you're going to interlace, like physically interlace, to making these motions very awkward, your weft. And the quality of your cloth and what it looks like is going to depend on how exactly you're interlacing those two things together. And so we see on the right hand side is something called balanced weave, and it's actually called plain balanced weave, where the weft and the warp are of equal thicknesses. They're equally spaced apart, and so you're going to be able to see them both when you actually look at your final cloth. What you see on the left is just an example, but it's something called crockbard, which is a Scandinavian type of weaving. But basically your weft, it's much thicker than your warp. And so you're only going to really see the weft, and it's packed very densely together. You're really gonna see only the weft in the final piece, I think. And so there's tons to do to analyze these things when, even when they're different thicknesses, etc., how they're gonna hold together. But even if we're just talking about balanced weave, where they're both the same weight, same thickness, same spacing, everything, there's still a lot to do. So if we let's just concentrate on balanced weaving so that we don't overcomplicate things. But even with just balanced weaving, how you do that over under interlacement is gonna really rule what your final cloth looks and feels like. So if I go over under, it's gonna be very tight. And if I go like over under, then it's gonna just look and feel different. And so really the pattern that I make is controlled by how I interlace those yarns. And now because people didn't want to live their lives doing these with their arms the way I'm doing right now, they have invented many, many different machines, and they have evolved and become more and more complicated in order to make the process much, much quicker. Like imagine doing a whole shorts or whatever, like it takes forever if you have to do it by hand. And so one of those innovations is the shaft loom, which is still in use today a ton. And basically what you have here is you have these shafts or frames that you pass the yarn through. And then when you lift one of those frames, you lift the subset of yarns that are connected to that frame. And now you can just pass your weft through. And so you have some yarns that are lifted, some that are not lifted. You pass your yarn through, and then when you unlift them, then now you sandwich them, and instead of having to go over, under, now your weft is over whichever ones were not lifted and under whichever ones were lifted, and that's how you can speed the process up. And so when you're setting up your loom, you basically, at the beginning of time, you have your warp, which we have right here, and then you have to decide before, you have these petals, which are like little needles. You have to pass each one of the warp threads to one of these needles. You have to decide which one, and you decide which, like, in which frame I'm going to connect that specific thread. Which one you connect it to is going to really rule the pattern that you have at the end, because all of the threads that are going to connect to frame one, for example, are going to lift together or lower together. All of the ones that are connected to frame two, again, lift together or lower together. And so so how you connect them is going to determine the amount of patterns and the kinds of patterns that you can make. And then the other tool that you have available to you, because people didn't want to be like reaching over and lifting frames, are pedals. And so you can really, the way you weave is you push on those pedals, which lifts frame up, depending on which ones you connected to which pedal. You usually have more number of pedals than you have of frames or shafts. And so when you push a pedal, it'll lift up the subset of frames that you connected to it. And that's basically how you can connect one or two or however many you want to that particular pedal. And so it's actually pretty complicated to plan out your weave. And so, and the other thing is that it takes several days. Like, it's not trivial at all. You make a mistake, you have to start over, it kind of sucks, you have to keep tension in the threads. It actually takes like a couple days to do it. And so what weavers have to help them out is a weaving draft. And a weaving draft totally dictates how they have to set up their looms and what they have to do at each time step in order to achieve the pattern that they want to achieve. And so let's look at the weaving draft very quickly. And so the first part of the weaving draft is the threading, which, as you can already see, because we're talking about math, really looks like a matrix, like a binary matrix. And then you can think about it as an F by N matrix, where F is the number of frames that we have, and N is the number of threads that you're going to have in your final pattern. And then each one of the rows tells you which thread you're going to connect to which frame, right? So you can have one thread per in each. One thread can go to one frame. Then the next little matrix that we have is your tile, and that's a frame number by petal number matrix, which tells you which frames you're going to connect to which petals. And then the next matrix is your treadling matrix, which tells you basically a time step or length of your cloth by P number of petals, and it just tells you which petal am I going to press at which time step in order to achieve my cloth. And then at the end, we have our drawdown, which is the end, kind of like what my pattern, like the end representation of everything. So you can clearly see my drawdown is really just the matrix multiplication of my threading, my tie-up, and my treadling matrix. And now that we have what we have here, which is pretty awesome, is a very visual and physical representation of this matrix multiplication. So we teach a class now where we can pause, where we can give an introduction to linear algebra to artists and undergrad engineers, where we posit problems like, for example, like if you want to create this pattern and you're restricted to this many frames, what is your actual matrices that can achieve that, right? Or if you can only have this tile, what can you do, what kind of patterns? Or if you want to create this pattern, but it's not possible because of your threading, what is the closest pattern that you can have, right? And so let me give an example of that. The important point here is that like each one of the matrices has a very physical representation. And so when you're doing the operations, making a mistake is really obvious because there's a physical representation to what making a mistake is. And there's also your set of constraints are also very physical. In this case, for example, say I want to do, this is something called a twill weave. And so when you're thinking about like, oh, like there's like so many different possibilities for what my treadling and my threading should be and my type, right? Like there's many different matrices combinations that are going to achieve it. But when you're starting to plan out a weave, then things that you think about, for example, is number one, the easiest thing for me to do to thread a loom is if it has a very distinct pattern, if it basically kind of looks like an identity matrix. So if I have a threading where I have to go the first thread to number 4, and then the next one to number 2, and then I jump over to, then I'm always gonna make a mistake and I have to start over. So the first goal is like, okay, can I make the simplest threading possible? And then that will help me in my threading. And then the other one is also the thread length. Is like at each time step, I wanna, if I'm following a pattern, it's much easier for me not to make mistakes than if I'm not following a pattern. So if I just like go 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, that'll be super easy for me not to make mistakes, make an awesome weave. So then, and so this is a problem like from class where we tell them like what are the simplest threading and threading matrices they can create, and what's your type gonna be in order to make this happen. And so then students solve the optimization problem, and then they experiment, and then it's okay for the type to be complicated because it's just something that you're gonna do one time, and then that's it, right? There's a bunch of other like hidden amazing math concepts that you can teach with these, where, for example, like if you want to create just any random pattern, you don't even know where to start doing your, doing your constraints, like can I even make these, etc. The rank of the matrix actually tells you a lot. So the rank of the matrix here tells you that you need at least 4 frames to create this pattern. If you don't have 4 frames, so there's 4 independent sets of vectors hidden in this pattern. If you don't have at least 4 frames, you can't even start creating this pattern, for example. And so with that, you can start thinking about it. There's a lot of other mathematical constructs that don't necessarily relate to linear algebra that are hidden in weaving. I was so lucky because like in the 80s, I don't know why mathematicians went crazy for weaving and started analyzing everything about it. But another amazing thing is a lot of the times you don't actually realize when you're first, if you just have a weaving draft, it's impossible to realize without analyzing it, whether you're gonna weave one cloth or multiple cloths out of it. So you really need to analyze the interlacings in your cloth to make sure that everything is interlacing with everything. And or you're doing a technique called double weave. And so this may not necessarily be not wanted, like if you want to make pockets or something, this is something you actually want to do, but it would be good for you to know that you're actually doing that. And so we teach a little bit of set theory and a little bit of introductions to proof by induction and by contradiction through analyzing whether cloth is going to fall apart or stay together as well. So there's that also. And then there's a ton more that I don't have time to get into, but the other aspect of weaving, as I mentioned briefly before, is that it really pushed technology forward. Our very, very first computer that existed was actually a weaving machine. I didn't know that. So, as I said before, like people want to create more and more complicated things. You're restricted by the number of shafts and pedals that you have. So the best weaving machine that you could possibly make would be one where each one of your threads could move independently, right? But then how are you going to keep with that? There's actually a very funny, I should put it, but there's actually a funny picture from in medieval times when people did make such a machine, and there was actually a boy, like it was called that, like a boy whose job it was to be on top of the machine and like go and pull all the like little threads at each time step because it was so hard to keep track of which one. So somebody had to keep track of all of them. And so it wasn't too long before somebody invented a system, the punch card system. The first time it was used was for weaving machines, where you have an actuator, each thread is controlled by one actuator, and then what decides whether the actuator is going to actuate or not is going to be a construct where if you have a hole, the actuator passes through and it lifts, and if you don't have a hole, then the actuator doesn't pass through and it doesn't lift. So that was actually our very first computer. Okay, so now that we have all of that, we have like an amazing art form, and we have all of these math relationships hidden in that amazing math art form, and now we have a robotics also connection to it. What we did is we really wanted to teach a class, kind of like an introduction to robotics class for everybody to try to motivate artists and people who normally maybe would not be encouraged to go into robotics, The first problem that we had to solve was making one of these weaving machines. So the jacquard looms, like those that actually individually are hundreds of thousands of dollars. Frame loom is thousands of dollars. We can't really have that in class. So we built our own little loom. But it's not that little. It has 40 threads, so it's enough to do a bunch of fronts and to make nice art out of it. And we built it as a kit. And so the idea is that students build it in class. We get them into interdisciplinary groups where we have, engineers and artists working together to build a robot and to work together programming it and to work together weaving with it. And then we have a bunch of lessons where we combine some of the art, some of the math, some of the robotics, and students weave on these robots. And and we teach them some vector math. There's a lot more math analysis in the weaving that I had time to get into, but just in robotics, the basics of circuits, basics of motors and computation, and also weaving and as an art form, the history of it, and a bunch of little patterns.
So the name of the class is Recrafting Soft Technology?
Yes. What do you think about that, Kevin?
Well, I guess I don't know what the class is about if I read that. It sounds interesting, but I haven't had class
Just
about.
to get them in the room.
What sorts of students would take that class?
Yeah, so we have from all over. So we have a combination of like artists, musicians. We also get like engineers. We get graduate students. It was really designed for undergrad. My hope was undergraduate freshmen, and my hope was to get the artists soon and to be like, you can also do robotics. But really, we also get graduate students. We get from all over. Yeah.
How do you grade them?
I just give everybody an A, honestly. They have projects, yeah, they have projects and stuff.
Delighted to hear this honest.
That-
It could be a really difficult.
They have
course.
projects and stuff, and like, yeah, and they do it or don't, I don't know. Yeah, no, and they have interesting projects, they work together. Part of it is also, we're also studying like how they work collaboratively and in everything and in these interdisciplinary teams. Sometimes there's conflict, sometimes it works great. But they make interesting projects. They also learn a bit about like wearable technology and when we teach about circuits and how to connect things and yeah, and
Do you have
yes.
students like who don't know about vectors and matrices?
Yes.
And so question one is, do they learn it?
Yeah, that's a good question. Some of them do. It is a little, that's something have to work on for the next iteration. Because something that you have to be very sensitive about that I didn't think about is some of them like don't want to learn it. Like they're artists because of a reason, and they're very proud of the fact that they're artists, and they don't want to be told that like there's something they're lacking or anything. But what's very interesting, especially in problems like this one, where the way I think about solving this problem is I use set theory and I go through and figure out what are the sets of strings that will separate from the other sets of strings. And that's the way I think about it. Well, a lot of the artists, the way they solve it, actually, and I still don't really understand what they did, but most of them were like, yeah, obviously it's gonna separate or not based on how it looks. Like they just like found a pattern in
I
it.
didn't really follow what was going on here.
Yeah.
Going on here?
Yeah, so here, yeah, absolutely. So here, so what you do is when you say, okay, so imagine you have like these, you just see a pattern and you weave it, and in the end it separates like this. And so it's like, how do you figure out if that's gonna happen? So basically what that happens is you found a set of strings A that never interlaced with another set of strings B. And so you can prove that in many ways. One way is, can I find a set of strings A, for example, that if they're under a string, it's only under a string A. And, or you can think about like B never goes over A. And so if you find that, then they will separate, right? And it happens frequently where you see a pattern and you think the interlacing are gonna work out, and then they don't. But for the art, a lot of the artists, they don't need to do that. Once we told them, they just like look at it and they're like, oh yeah, obviously. Because apparently there's like an L pattern or something. And if they find that L or something, I can't remember what, but they told me, they were like, yeah, there's an L or a T pattern or something. And if you see that, then they're gonna separate. And I was like, okay.
Wait, I don't get it. Is the picture on the right supposed to be reflecting what's happening on the left?
Yes, it's the same thing. And so what you do is, so if a string is under, so basically, if you see, if you have your warp and you have your weft. And so when the weft is over or the warp is under, you put, yeah.
But I see pink vertical bars in that
Yeah.
picture, and I see
Oh, yeah,
green
sorry.
vertical bars in that picture. And I don't see any green vertical bars in the video.
No, you have, oh, sorry, so these, okay, horrible choice of colors, okay, the B's and A's are just doing the subsets, the vertical strings are just pink and the horizontal ones are just gray.
So there's no correspondence in the color.
No, in the
between
colors,
the
yes,
two.
and so
the-
terrible
I
colors.
should imagine the 4 pink strings.
Yes, the
As the
pink
4
strings.
vertical strings, regardless of their color.
Yes,
And I should imagine the 4 horizontal strings as the
Yes,
4 horizontal strings.
exactly, and so if you have a horizontal, every time a horizontal string is over a vertical one, you put a 0, because that's kind of how you create your binary matrices of these also, like, if you actuate it, there's a 1, and if you actuate it, then the vertical string is gonna
Why
be over.
is in the top row?
Yeah.
Why does that second cell have, in the top row,
This one?
top row, the second column, why is
Mhm.
that a 0 and the 1 in the third column, why is that a 1?
Yes,
What's
and
that?
so,
why
yeah,
is
and so
that?
what that means.
No,
if you-
stay all in the
Yeah,
top row,
0 and 1.
1,
You
why?
can't see the picture underneath, but what that is depicting is just that so in each one of these cells, so here, the weft is over the warp, so there's a 0.
Okay,
And when the warp is over, there's a 1.
what, under?
When the warp is over, there's a 1. When the weft is over, there's a 0.
0, I see,
Yeah.
okay, so so the 1s and 0s reflect whether it's over or under.
Yes,
But I see,
Yes.
okay.
Physically, it's the one means that when you are running that weft,
yes,
you have lifted where the warp where there's
Yes.
a 1 and not where there's a 0.
exactly,
So, yeah.
yeah,
So like on that, so, and you do that for the top one and then you advance
to the next one,
double cock, whatever it is.
Yeah.
And
Yeah.
you lift, like here on that second row, you
Yeah.
lift all.
you
three.
lifted these 3, yeah. And here you lifted these 3, and here you lifted just this 1.
Cool, and if you, we've done that, then you repeat that pattern over your whole thing, that you've actually done two fabrics.
2 fabrics instead of
one.
just 1, yeah.
Wow.
Because here, the way I solve it is I go column by column and I ask myself, okay, like if these were a set of A, if these were an A, can I find a B that would go over it? And I go through and I solve it like that. But then artists did not want to learn that way, and they just developed just an intuition where they were just like, oh, obviously, like you see this pattern, it is gonna be 2, and you're like,
Where would the artist need to go beyond that type of intuition?
They don't, if they stay artists. Like my hope, I mean, I don't know. I have different beliefs, but I believe the world is burning. And I believe we need all sorts of folks to solve it. And I would like to see more folks with maybe like a kinder soul go into robotics. So I want to encourage artists to also go into robotics and maybe solve some of these problems also.
Artists are mean, like Picasso. I mean,
Not necessarily artists, but
it's also subjective, so it's all egos. It's all artists. Aside from people are nice, because I think there's some objective criteria by which you get estimated.
like scientists, you're gonna be talking to them, you're like, why are you here? And they're like, because I want to be challenged. And you're like, I mean, there's, we're eating plastic all the time and we need energy. And it's like, come on, man. Yeah.
Like, what did the dynamics end up being like in class? Do you find that the artists, or first off, I was curious how long it took to build that machine, but did you find that the artists kind of stayed away from all the coding and stuff, and then the people that were good?
Collaborative, yeah, it was actually pretty awesome. No, and they were very interested in like, that's why I said like, I'm still learning how to exactly teach this class. I think it has a lot to do with that. But they were very interested in weaving and in making their own robots. They all wanted to keep it, which so like keep it But and then having a machine that because yeah, usually so a software, so the machine also comes with a software and they learn how to program it. If you just buy a license for a weaving software, which literally is just doing those matrix multiplications, it's thousands of dollars a year, which is crazy. And so just having the ability to just now make their own patterns, they were actually like pretty excited by that. It's the more like step that I'm working on is like how to actually like because it's not just artists, right? Like I got architects and designers and get people from all over. It's like, oh, now you can also, don't let math like be a block for you to like if you don't want to, it's fine. But most of the people that I talk to, they usually tell me like, no, I'm very bad at math. Yeah, I want to show them that it's not true.
How many times have you taught this class?
Just once.
And there's one robo loom?
No, well, one per group of 4 students. So right now we
They
have
built it?
7. They build it.
They built, so when you start the course, they don't have one, but they have the plans, they built one,
Mhm.
they start using it for things.
Yes, yes,
And then when you teach it again next year, if you do,
yeah.
now you're gonna have 11 robo looms?
No, like we disassemble them and like, yeah, the 80/20 is pretty expensive.
So they take them apart and they put them back together.
Yes, at the end of the class, I make them take it apart. I think it's a good lesson, like, don't
Can
be
you
too.
just sell them?
don't know. I'm not a business person.
Fund your-
You guys should make a company. You guys are, you can make a company. I'm not business savvy. Yeah,
And like, how many weeks did it take them to build that?
2 weeks.
2 weeks?
Yeah, it's like 2 class. The classes, I chose like the 3-hour time slots, like one big class. I do a flip classroom where they watch lectures. And so it's like they take them 2 classes, so like 6 hours to build one. But yeah, but it takes you easily like 20 hours because I had to thread one like of those, those other like looms. And mostly it's because of the tension you have to be keeping all the time. And if you make one mistake, you have to start over. So. Yeah. Yeah.
Like, engineers are getting excited about weaving.
Oh, really?
Right? Oh, yeah, you see lots of stuff, people. Oh, yeah, you start to see like, more soft robotics people doing stuff with weaving, running wires and doing electronics
Mhm.
and so forth. I'm wondering if you see this getting sort of another
Another
dimension.
dimension. Yeah, so I do, one of my collaborators at Jim is does his whole research is on weaving and doing things. So he got involved and he wants to we think maybe of adding another level so he can do like 3D structures basically because that's what he does, like analyze. He's a graphics guy, how to do like 3D structures based on it.
Yeah.
So yeah, we can do that.
Oh, that, oh,
Yeah. Yes.
Do you know like what percentage or how many students, like pure art students come into the class and then leave the class wanting to adopt technology or start
Oh,
integrating?
that's
technology?
interesting. Yeah, because I just finished teaching the class. But it would, yeah, following up might be interesting. I don't know yet. Yeah. Yeah. Yes.
So the robo loom is just basically a miniature version of the machine that they will be using in the industry. When
Yes.
They want to make like
Mhm.
yeah, okay. That's
Like a real cross. Yeah. Yeah, and it is technically a jacquard loom, and so for class, we constrain it, like we tell them like, okay, like for this problem, you can only use these many shafts and like behaves as like a shaft loom and stuff like that.
do you have a video of it operating?
Yes. Wait, no, wait, yes. Yeah. It's a little slow, but it's okay.
I see more, where's what, oh, they're doing the what by hand?
Yeah, oh yeah, sorry, yeah, they physically weave, yeah,
Yeah.
that was a design choice. I really think like if they have no physical interaction with it, I don't know, because the weaving is actually pretty fun if you do it. If you just like push something and have the robot just do it for you, I don't think it would be the same.
Okay.
Yeah.
Yeah, okay.
Yeah. Fun.
I mean, like jacquard looms will just do everything for you, but then I don't know, it's educational. Yeah, this work is done with a ton of collaborators and students, not just on my work. Part of it's funded by the NSF. And if you guys have any other questions, before we have some discussion.
Any other questions? Thank you so much.
No, thank you.